This video looks at a problem-solving technique in the context of first-order responses. Now, previous videos introduced a technique for problem-solving. That is, how do we tackle problems which are not a simple reproduction of exercises and things we've done in the notes and lectures, or tackle problems that are somewhat open-ended, that is, they do not have a single correct answer. And our proposal was to use a simple iteration through 3 steps. First, ask yourself, what is the topic? And make sure you know everything relevant about that topic. So what are the key formula, the key laws, assumptions, conventions, etc., etc. Because it's likely that you'll need to apply these in order to solve the problem. Next, look at the information you've been given and see if there's links between this information and what you know about that topic. And you can then use these two together to create new information. Finally, with the new information you've just created, you might want to iterate back through steps 1 and 2 to generate even more new information. Now here's the key at the bottom. The ability to solve problems is a skill that's highly prized by future employers and the thing that you should focus on most during your degree studies. So, just an illustration. Step 1, you expect students to list what they know, and therefore it's implicit that students have a comprehensive awareness and competence with the core knowledge for any given topics. You will not be able to do problem solving if you've not got good competence in all the key formula and assumptions, etc., etc., for a given topic. You need to have to hand a list of all the tools that you might need to use for a given topic. Now that could be sheets of key mathematical formula or engineering formula or laws, etc., etc. So I recommend that you have these to hand. Make sure that you can get them quickly when you need them. So we're going to illustrate this with a simple example based upon first-order responses. So here's the problem. You need to choose a central heating boiler. So the house owner wants to purchase a boiler to heat the house, and they've got some approximate parameters for the house. For example, they think the capacitance of the house is about 36 megajoules per degree, the heat loss to the surroundings, 20 kilowatts per degree, the cost of gas, 50p per kilowatt day, so that's if they use a kilowatt for a whole day, it'll cost them 50p, and the cost of a boiler is £1,000 up front, plus an extra £100 for every extra 10 kilowatts of power that the boiler delivers, and you can have this in multiples of 10 kilowatts. So which boiler would you buy if you were this house owner, and why? And you can see this question is somewhat open-ended. It's not said find number X or find number Y. It's asking you to think a bit more like an engineer. Look at this scenario and think about which boiler would you need if you were the house owner. So first of all, we start with what do I know? Well, for a standard heating system, there's heat supplied, there's heat lost to the surroundings, and there's heat stored. So therefore, if you want a simple model, and we're not trying to do anything complicated, you're going to get a model a bit like this. You'll see W. How much heat are you supplying to this house? That's what's coming from the boiler, and here I've called it W. You've got how much heat is stored, and here I've done a rate of change of energy stored as C, the capacitance, times dt, where capital T is the temperature. And then you've got how much heat is lost to the surroundings, so that's some K times the temperature of the house, T, minus TO, the temperature of the surroundings. So you see you get a very simple first-order model represents this system. So that's dealt with what do I know? And that's where I would start before we even read the rest of the question. I would write this down so that when I get the question information, I can see how it's related. Right, also what do I know then? Well, if my model is a simple first-order model, then I know what the dynamics are like. So perhaps it'll be interesting to look at that before I start. So here's a standard first-order model in time constant form. You can see alpha is the time constant. Ku will be the gain times the input, and Ku together gives you the steady state. So if I solve this, you'll see I get that formula there, but it's probably easier to plot it And what you'll see is you have an initial value and a final value, and the final value is given by that KU term. And then the only question is, how quickly do I go from the initial value to the final value? And there's a way of working that out which I'm not going to dwell on, but what you'll see is you end up with a time constant, and alpha is somewhere around here. I'm being approximate. Okay, so this figure is illustrative only. And what you can see is the time constant is around 40 minutes, and the steady state KU must be 20. So why have I done this slide? Because before you start tackling this problem, make sure you understand first order systems. Make sure you understand the link between the parameters in the equation and the behavior that you get. So here's my equation that I actually derived in terms of what do I know. I said I had W equals C dt dt plus kt minus t0. And I'm going to rearrange this into my standard, and if I put this here, my time constant form. So I'm still looking here at what do I know, and what I know is if I put my first order model in standard time constant form, then I know how it behaves. So there's my time constant. It's this capital C over K. And there's my steady state. It's this term here, W over K plus T0. So I haven't used any of the information from the question yet, but I've understood a lot about the topic. Okay, so now that I'm clear what I know about the topic, next I can look at the information supplied and the problem to be solved. So this is the information I was given. Thermal capacitance 36, heat loss 20, cost of gas, boiler cost, and so on. And I wanted to know which boiler would you buy and why. So the next step is to use this information I've been given and combine it with what I already know about the topic and see what that tells me. So the thermal capacitance 36, heat loss 20, and that was the parameter C, and that was the parameter K. So I can put those straight into my equation. So here was my model for the system. If I put in that C and K, then this is what I end up with. W over 20 plus T0 equals 36,000 over 20 dt dt plus T. Now, the units of this are perhaps not ideal, because what you'll notice is that usually people will express T in seconds. And if you're talking about the heating of a house, actually using seconds is probably not a very sensible unit. It's too fast. So generally speaking, what people might do is they might say, if we're talking about house temperature, why don't we use hours rather than seconds? It's a bit more meaningful. So if I change the units of time to hours rather than seconds, you'll see the left-hand side doesn't change, but the derivative bit does change, and I end up with this. 0.5 dt dt plus t, and that looks a lot more sensible. But what have we got? Just to remind, based upon what we said we knew at the start, this is the steady state, W over 20 plus T0, and this 0.5 is the time constant. So I'm restating that now. You can see the steady state, there it is, and the time constant is 0.5. So if the time constant is 0.5, it tells you the house will heat to steady state in about 2 hours, assuming the heat supply is constant. And you might say, yeah, that sounds about right. I'm quite happy with this. This model seems reasonable. The steady state is going to be W over 20 above external temperature. You can see here's the steady state, W over 20 plus T0. So the distance above T0 is W over 20. Now, if you imagined it was freezing outside, so T0 was of the order of 0, and you want an internal temperature of around 20 degrees, you can immediately see that W needs to be somewhere around 400 to 600 kilowatts. Okay? So what have I done there? I've used what I know about first order systems, I've plugged in the data, and then I've added a bit of common sense, a bit of engineering. I've said, I know what I want the internal temperature to be. If I bring this into the problem, I can create a new piece of information, and here's the new information. So the boiler needs to be of the order of 400 to 600 kilowatts. Now what else am I given? Well, I was given the cost of gas, 50p per kilowatt day, and the boiler cost. So let's have a look and see what happens if I put those in with what I've already done. The boiler, if we assume it was something of the order of 500 kilowatts, so if you were running at 500 kilowatts all day because it was rather cold outside, what you notice is the cost of the gas becomes £250 a day during freezing weather. I think you might be a bit concerned about that. And you'll also notice that the boiler cost is about £6,000. And so what you'd be doing as an engineer is you'd be saying, this cannot be right. Nobody pays a bill of £250 a day for their gas. They do pay a lot, but not that much. And £6,000 does seem a bit steep for a boiler. There's something not right. And that's a key thing about problem solving, that you need to have the skill to spot when things aren't right. So what was the underlying question? Which boiler should I buy? And this is encouraging students to analyze the whole scenario and apply some engineering know-how. So what have we got? The daily cost is clearly outrageous. So either the cost of the gas is unrealistic, or the heat losses are estimated to be too high. Those are two obvious errors, things that you could chase up and say, there's a problem here, and I need to find out why. The time constants seem reasonable. However, if you're going to tell me that the heat losses are not right, then you're going to be changing one of your parameters, perhaps C or K. And because the time constant is given as C over K, as soon as you change one of those, then you're going to be wanting to be changing the other, otherwise your time constant will no longer be about right. So let's look at an alternative scenario. What if the heat loss to the surroundings was 2 kilowatts per degree, rather than what we said before? Then when I change the model, putting K equals 2, this is what I end up with. So what do you see? The time constant is now 5 hours, so the house will heat to steady state in about 20 hours, assuming the heat supply is constant. And you'd probably say, well, that's rather slow. The steady state, which is this term over here on the left, is now W over 2 above external temperature, and that means that W can be the order of 40 to 60 kilowatts to maintain a reasonable inside temperature. So you can see by changing K, by saying there's clearly something wrong, let's investigate what happens if I change one of those parameters, and that's what I've done here. Changing K changes the time constant, changes the boiler requirement. Now, in this case, the boiler power seems more reasonable, that's what you'd expect, but the daily cost is still of the order of £25 a day during cold weather, which is still rather higher than you would expect. So that tells you there's still something not right here, and the thing that's not right is clearly the cost of the gas was not a realistic cost, and you can get it much cheaper. Okay. Also, a time to steady state of 20 hours is clearly unacceptable. That's too slow. Now, let's go back to the overall issue about what is problem solving. The way we posed the original question was perhaps not very good. Usually, an engineer would begin from a specification. They would say, what is it I want? And then they would move to the solution. So let's give an example of what we might do. We'd say we want the steady state to be at least 25 degrees above external temperature to allow for the outside being, for example, -5. The daily cost should be at most about £10, and that was if the heating's on constantly, which it wouldn't be normally. The house should heat up in about 2 hours. And in essence, what you'd be doing as an engineer is you'd be saying, this is what I really want. So now I need to be asking myself, how can I make sure that this can be delivered? So write down what we know and link it to the specifications. So this is what we know. This is our approximate model for the behavior of the house. It's a first order system. Okay? We want the steady state to be at least 25 degrees above the external temperature. So what that tells you is this. W over K must be greater than 25. So you have two choices. You can increase W, and that will make W over K bigger, or you can reduce K, and that will make W over K bigger. And the best option, clearly, in the long term, is to make K as small as possible. Now, the maximum daily cost of £10 implies that probably you need cheaper gas, but it also tells you that the W you should be using has to be less than or equal to 20 with the cost of gas that we specified. If you want the house to heat up in about 2 hours, then this is what you need. C over 3,600K is less than 0.5. And what you'll see is we've come up with 3 requirements. This is what you need to meet in order for your heating system to be satisfactory. If you combine those, you can see W less than or equal to 20. Generally, I'm going to go with 20 because if you make W too small, you're really asking too much. W over K greater than 25 is going to tell you if W is 20, K has to be less than 0.8 kilowatts per degree. And that tells you what insulation you would need, but you might be asking, is this level of insulation actually deliverable? Okay, and in terms of the time constant, you're going to end up with a definition for what C should be. And of course, you're then going to ask, well, actually, can you control C? It depends upon the building, and it will be whatever it is. But notably, what you'll be spotting about everything here is something wasn't right in our original data, because if you're finding these requirements are inconsistent but reasonable, then something's wrong. And you need to go and say, well, what is wrong? And probably, in this particular case, what was wrong was that we had a totally wrong price for the gas, and that led us astray everywhere else. So conclusions. The video has given an example of problem solving. A simple approach involves key steps. First, say what topics might be involved, and make sure you know what you know about this topic and write it down. You'll notice for this case we spent about 3 pages writing down everything we knew about the topic before we started. Then, what information have I been given, and can I use this in combination with what I know? And then finally, start looking at what have I actually been asked to do. Okay, now I've got all this information together and I've written everything down. Let's look back at the fundamental problem. Sometimes you'll find that what you've been asked to do won't work, doesn't make sense, and it's okay to be critical of assumptions, because that's the whole point about problem solving. If something doesn't work, say so and say why and give your reasons, because that's what a good engineer does. Finally, just remember that real problems don't tend to have clean, analytic or unique solutions, so don't expect them.